This is Math 251, and we're in section 6.5. We are going to move on along. We've been spending several sections talking about those volumes of the surfaces of revolution. We'll continue with the geometry theme, but instead of talking about volume, in this section we're going to talk about length, specifically the length of a curve. So we call the length of a curve arc length. And of course it's difficult to measure because in general we've got formulas for things that are straight lines. We can either measure them directly, we can use things like a Pythagorean theorem or a distance formula, as long as we've got straight line distances. We don't have those wonderful formulas when our lengths are along a curve. The only exception to that would be a circle. If we've got a piece of a circle and we know the radius of the circle, we can usually use a little bit of a formula from trigonometry, things like that, to find that arc length. But in general, what about the length of an arc of some random function? Okay. In order to figure out the formula that we'll need to use, we're going to use a little bit of a trick of imagining that we're going to zoom in to the point where our curve turns into almost a straight line. If you imagine pretty much any curve, right? If you look at a small enough piece of that curve, a small enough piece anywhere looks like almost a straight line. Right? Any of those little tiny pieces are almost straight. So let's imagine we've just kind of zoomed in on a little tiny piece of a curve. I'm going to try and figure out the length of the arc from this point to that point. And since we've zoomed in so much that our curve is almost a straight line, we're going to approximate the little piece of arc length, this delta S, as the hypotenuse of this triangle. They're not quite the same, but if delta S is small enough, they're very close to the same. Eventually, we'll use our standard trick of shrinking everything down infinitesimally small, so the approximation will become exact. All right, my delta S, my little piece of arc length, approximated by this hypotenuse, is supported by a little piece of horizontal line in the x direction. We'll call it delta x, and then a little vertical line, vertical direction, so we'll call it delta y. I'm going to simply write down the Pythagorean theorem for that triangle. So I would have delta x squared plus delta y squared equals delta s squared. To solve for delta s, I'll just take the square root. And of course the square root of delta s squared. And actually, I was going to say that's just delta s, but I'm going to leave it like that because of the algebra that I'm going to do in the next step. Next thing I'd like to do is I'd like to divide through this equation, both sides, by the square root of delta x squared. On the left-hand side, I'm going to divide both terms under the radical. So delta x squared divided by delta x squared would just be 1. And then I'd have delta y squared over delta x squared, or delta y over delta x squared. Right-hand side, I'm just going to leave it the way it is, other than just combining it into a single radical. Delta s over delta x squared. All right, at this stage, I'm going to make the assumption that since we eventually want our approximation to become exact, we're going to let delta x become infinitesimally small. We'll call it the differential dx. Similarly for delta y, and for delta s. As delta s approaches ds, delta s, the hypotenuse, becomes ds, the actual arc length. All right, let's make those changes in our equation. Delta y over delta x then is going to become dy over dx. And we've reached our derivative. Similarly over here on the right-hand side, ds over dx, and we've reached a derivative there as well. And of course on this side I can simplify. Taking the square root of the square, I just have ds dx. All right, a little bit of algebra. I'm going to multiply both sides by dx. Squeeze it in there so these go away. And then I'm going to take the integral of both sides. On the right-hand side, that's like the integral of 1 ds. So I'd get 1s, or just plain s. And that's going to be the integral of the square root of 1 plus. Another way of writing dy dx would be f prime of x for our whatever function we're working with, squared dx. If I integrate between some limits of integration a and b, we have just found s, the arc length. For any curve, y equals f of x, between the point where x equals a and the point where x equals b. So this is going to be our arc length formula. It's the formula we'll use every single time we want an arc length. What's really nice about this is, unlike all of our volumes for solids of revolution, this is one single formula that's going to work for us every time. And so there's actually going to be a lot less prep work to get integrals set up in this section than there has been in the last couple. All right, here's our formula written out as a theorem. This is the one we just finished deriving for the function given by y equals f of x. I'll also notice that if you happen to have x equals g of y, if we've got a function of y instead of a function of x, it works the same way. Okay. The only thing that's required is that the function itself had to be continuous and in fact what we call smooth. The derivative has to exist. There's no undefined derivative, so no little sharp points or anything on our curve. It has to be a nice smooth curve. All right, so let's go ahead and try this out. I'd like to find the arc length for the function y equals x to the 3/2 on the interval from 0 to 4. It's not absolutely necessary to draw these because there really aren't any decisions to make, but just for the heck of it, I won't draw all of them. Let's draw this one. This is x to the 3/2. And you can see we've got, kind of looks almost like 1/2 of a, not quite parabola, but close. So we would have, drag this over here, let's see, almost there. At 4 we're at 8 it looks like, and that would make sense. 4 to the 3/2 is 8. So in my picture, I'm going to go from 0, 0 to 4, 8. We've got that curve kind of joining them. Okay. So it's this length that I'm trying to find. And I'm just going to do it since I do have y as a function of x. I'll use the top one. My arc length will be the integral from a to b. In my case, that would be from 0 to 4 of the square root of 1 plus f prime squared. F prime here would be 3/2 x to the 1/2. And we're going to square that dx. Many of these integrals actually can't be done by hand. This one can, so let's go ahead and do this one. Let's see, that would be 1 plus, squaring that would give me 9/4 x to the first. So if I just make a little u substitution here, u is what's under the radical. Du dx would be 9/4. Move the dx on over here, and I'd have 4/9 du is equal to dx. So my integral becomes the square root of u, and then I'll replace the dx with the 4/9 du. The 0 and the 4 are x values, not u values, so I won't put them in right now. That's u to the 1/2, so when I integrate, I'll get u to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So I have 8/27 times 1 plus 9/4 x to the 3/2. And now that I've got the x back, I can put the 0 and the 4 back in. So we've got 8/27 times 1 plus, if I plug in 4 here, the 4's will cancel, so that's just 1 plus 9 to the 3/2 minus 8/27. And if I plug in the 0, I just have 1 plus 0 to the 3/2. I'm going to factor out the 8/27, and I'd get 10 to the 3/2, and then just minus 1. 1 to the 3/2 still being 1. So there's an exact answer for us. We could, of course, plug it in the calculator and get a decimal approximation as well. All right, as I said, many times you will find that what's under this radical is much more complex than this, and in fact the integral becomes either very challenging or even impossible to do by hand. So mostly we'll use the calculator to integrate here unless I specifically say otherwise. Let's look at a couple more. In example 2, we have a problem that we actually don't need the arc length formula to give us the answer, but we're going to go ahead and use it and just verify that we get the same result as we would have expected. The question is to determine the length of x squared plus y squared equals 1 using calculus, and then we'll just check with geometry. That's nothing more than a circle of radius 1, right? So my goal is to find the arc length of that circle, or in other words, the circumference of that circle. Okay. We'll do it using our arc length formula first, and then we'll just use the geometry formula for circumference to check. Okay. So, using the calculus method. Let's see here. What I'm going to do is I'm going to say, because of the symmetry, If I just found the arc length of the top half and doubled it, that would be sufficient, right? So I'm going to take 2 times the arc length of the top half. What that allows me to do is I do have to have my equation solved for y as a function of x. So I'm going to go ahead and do that. I'm going to say that equation is going to become y squared equals 1 minus x squared. So y would be the square root of 1 minus x squared. Notice I'm taking the positive square root because I only did the top half where the positive, or where the y values are positive numbers. The negative square root would have given me the bottom half. All right, so I'm going to have 2 times the integral of, and now I'm just using my arc length formula right here, this one. Let's see, my limits of integration would be from x equals -1 to x equals +1. And then I've got the square root of 1 plus, and then I need the derivative of this function squared. So my derivative would be 1/2, 1 minus x to the -1/2, and then I square all of that, dx. All right, so let's see here. Under my radical, I've really got 1 plus. Oh, you know what? Holy cow, I forgot my chain rule there, didn't I? You're probably all sitting there saying, oh, wait a minute, she made a mistake, and I did. When I did this derivative, I did the 1/2, and I left off the square here, which meant I forgot my chain rule. There should have been a times 2x in here. Times -2x, actually. All right, so let's fix this up and then we'll square in the next step. I can let the 2's cancel. So I'd have a -x times 1 minus x squared to the -1/2 squared dx. All right, now we'll go ahead and square. That's going to make that x squared. And squaring, I can multiply those exponents, so I'd have 1 minus x squared to the -1st. There we go. That's better. So make sure you get that chain rule in there. Don't make the same mistake I made. All right, I'm ready to go ahead and do this on a calculator now. So I'd have 2 times that horrible integral. It's actually doable by hand if you work really hard at it, but we're not going to mess with it right now. We're going to work with techniques of integration in a later chapter. So for right now, we're more interested in our setups. And even the calculator is having a bit of trouble with this one. I will show you why in just a moment. We may actually need to do a little bit more work on this now that I'm seeing it. Let's see if the calculator ever gives us an answer. You know what I think is happening here? The limits of integration from -1 to 1. Think about this term right here. If x is 1, what happens? We'd have 0 to the -1st power, wouldn't we? Putting 0 in the denominator, that's a problem. There actually is a way to handle that. It's called an improper integral, and we have not yet got the technique for doing that. It does take a little bit of work. We'll learn about this at the end of chapter 7, I guess it is. But for right now, if you let the calculator run long enough, it does indeed get us what we need. So it looks to me like we've got an answer here of about 3.1415, blah, blah, blah. Looks a whole lot like pi, right? Yeah, I think we got an answer of pi. All right, so 2 times pi, my final answer is just 2 pi. So the fact that that's an improper integral, as I mentioned, again, we'll talk more about it later. The calculator can handle it, but as you saw, it took it some time to do it. All right, let's check with geometry. The circumference of a circle is 2 pi times the radius, just a basic geometry formula. And so in this case, since our radius is 1, that makes it really easy. The circumference should indeed be 2 pi. And of course, that's exactly what I got, although it's a whole lot easier using geometry when we have something as simple as a circle. All right, let's try the next one. We want the length of x equals y squared for 0 is less than or equal to y, less than or equal to 3. This is just the inverse of the parabola y equals x squared, so it's going to be a sideways parabola. If you want to see it graphed out, we can of course do that pretty easily. If I just type in x equals y squared, there we go. And I want to go from y equals 0 to y equals 3. So it looks like right around here would make sense, right? If y is 3, x would be 9. So what I've got is out here at x equals 9, y is 1, 2, 3. I'm looking for just this piece of the arc length. That's my S that I'm trying to find. All right, so we will do our process again. Now this time, instead of y as a function of x, notice I've got an x equals a function of y. So I'm going to want to use this alternative form. I'll have the integral, I'll write it out here, c to d of 1 plus g prime of y squared under the radical. dy. So that would be 1 plus. The derivative with respect to y would be 2y. And this is a y integral, so my y values go from 0 to 3. All right, we're going to go ahead and use the calculator to integrate this one. And I get something, I don't recognize that as a particularly nice, doesn't look like it's a repeated decimal or anything. So rather than trying to make it a fraction, I'll just round it off to 3 decimal places. This is actually an approximately equal to, like so. All right, one more. We'd like the length of the function y is equal to 2e to the x plus 1/8 e to the minus x on the interval from 0 to ln2. By the way, in this last problem or two, I've always specifically told you whether I was giving you x values or y values. Notice that it is the values of the independent variable that you're being given. So if I don't specify, you should always assume that this is the interval for the independent variable. In this case, the input is x. So this would be x values. All right. We might as well sketch it. Again, the sketches here are not nearly as important as they were back with the volumes of revolution, but it doesn't hurt to know what we're looking at. My function is y equals 2e to the x. And let's see, I think, no, I guess they don't in this one. I think I can just type in e and I'll understand it. Plus 1/8 e to the minus x, or just e to the minus x over 8. All right, there we go. It's almost parabola looking, isn't it? We are specifically looking at the interval from 0 to natural log 2, so not a very big value. Here's x equals 0. The y value is about 2.125. And ln2, what is ln2? Is about 0.7, so we're not going very far. We're just looking for a tiny little section from about here to, where's about 0.7? Yeah, right about there, 0.7, 4.09. So let me sketch that. Oops, 2 here. And at 0.69, we were at, what did we say? There it is, 4.05-ish. So that's my 0.02, and this is about ln2 roughly 4.05. Just for reference. And we are looking for the length of the curve in between them. All right, again, the picture is really just sort of to satisfy our own curiosity. We don't need the picture to set this up. All right, in this one, we are looking at y as a function of x, so we'd be using the original form. Under our radical, we would have 1 plus f prime of x squared dx. And let's see, it's an x integral, so the x values would go from 0 to ln2. Also just given in the problem, of course. And under our radical, 1 plus, I need the derivative of this function, so that would be still 2e to the x. And then when you take the derivative of the e to the minus x, the chain rule will give you a negative, right? So that actually end up being a minus 1/8 e to the minus x, and that gets squared. Now I'm going to tell you, if you're interested, in your packet, in your answers, I have put the entire long algebraic method for doing this. It's possible, but it's a really lengthy method. If you're curious, look in your packet of completed notes and it's there. This is not, however, something that I would expect you to do by hand at this point. So I'm just going to say we'll get an answer here on the calculator. And I've got about 2.6. Actually, that looks like a nice fraction, doesn't it? Yeah, it's 33/16. Okay, so that is finding arc lengths. Again, not nearly as difficult as setting up the volumes for the surfaces of revolution. You don't have all those choices to make. The only choice you have to make is, are you using a function of x or are you using a function of y? Other than that, it's just a matter of following the formula. All right, that's all we're going to do with section 6.5.